Video, I want to talk about factoring trinomials with special cases. This video is a follow-up to the other one titled Factoring Trinomials when the leading coefficient is 1. Here are the two problems that we'll do. And to make sure we don't take ourselves too seriously, let's think about the fun question. How do you feel about thunderstorms? Okay, so this concept, factoring, falls under quadratics. Quadratics, it's technically anything with an x squared or variable squared. So quadratics is typically Algebra I, usually reinforced in Algebra II. Are quadratics on the ACT? Yes, they are. Okay. Under the standards for the ACT, I noticed that they included some special cases, and I have seen these on there before. These two special cases, well, I picked one of each here for the problem. So we have a difference of squares for the first one, and then this is a perfect square trinomial, and I'll explain why. So you may be asked to factor something that doesn't even seem like it could be factored. For this first one, it's a binomial. It doesn't really seem like it can be factored, but a hint that it can be is that we have a perfect square here and a perfect square here, and there is a subtraction symbol between the two. Okay, so if I think of the square root of p squared and the square root of 9, I get p and I get 3. And I can also think of this problem as basically p squared plus 0p minus 9. And all of a sudden, this becomes a lot easier because it's just another one of those factoring trinomial problems. So I'm going to erase this and relate this back to just factoring a trinomial. So I know that p would go here, p would go here. And I'm thinking about what adds to 0 and what multiplies to -9. Well, as you do enough of these difference of squares problems, you realize that if this is 3, then this will be -3. They are, it's always going to be 1 plus and 1 minus. You have p plus 3 and p minus 3. I could also get p minus 3 times p plus 3 as my answer. So it's called the difference of squares because these two terms are perfect squares, and the difference is the word that implies subtraction. So you think of those as perfect squares, you square root both of them, and you know that you'll get 1 plus and 1 minus. Because if you FOIL this out, you get p squared plus 3p, but minus 3p, and those two will cancel each other out to then give you a 0 for that middle term. So think of this as having a sneaky 0p in the middle. So a perfect square trinomial is different, but also relates to that just factoring trinomial concept, especially when a is equal to 1. It's the best way to introduce this. So if you see a trinomial, you should think, as long as it is factorable, that you can just break this off into two binomials. For this one, because this a or this leading coefficient is 1, we'll have n and n. And then we're thinking of what two numbers add to -10 and multiply to 25. So it's a perfect square situation because that 25 is the perfect square. The square root of that is 5. but I know that they need to add to -10. And so these numbers will be -5 or -5 and -5, n minus 5, n minus 5. And the way that you report your final answer is that binomial squared. Some students think that when you have this kind of going forwards, that would be just n squared minus 25, but you actually cannot distribute that 2 there. That's illegal in the algebra world, because you then would be missing out on this -10n term. So we have to think of this n minus 5 squared as the product of 2 just n minus 5s. So it's called a perfect square trinomial because you have that same binomial twice, and it's a perfect square altogether, because when you multiply it out, then it would become a perfect square. So I'm going to circle the final factored answers, and I recommend trying some practice. They match these situations pretty similarly. However, I made this second one, this difference of squares problem, a little bit harder, just to see if you can relate it to some of the slightly harder factoring problems where the a term or the leading coefficient is not 1. So try these. Give yourself a second, maybe pause the video. I will show you the answers. All right, answers. So we have m minus 4 twice as the first answer. And then this, if you think of the square root of the 4n squared, you get 2 and then an n, right? If you square rooted both of those. And then the square root of 1 is just 1. So your final answer for the second one is 2n plus 1, 2n minus 1 for that one there. A little harder. All right, let's finish off with a quote. This has nothing to do with math. It's just fun. A party without a cake is just a meeting. Julia Child. So I hope this video helped you in some way. And if you have any good answers to the fun question, feel free to leave it in the comments. I'd love if you would click subscribe if you want to keep up with more videos. Have a good day.